The universe is here. That single fact is already a problem, because by the rules we have discovered, by the equations we trust, by the balance of forces that govern reality, there should be nothing at all. No space, no time, no light, no story to tell. Look up at the night sky. Every star, every galaxy, every faint smear of light is evidence of an outcome that should have failed before it began. According to modern physics, the universe was born in an instant of unimaginable intensity, the Big Bang. Not an explosion in space, but the sudden appearance of space itself. And that's where the trouble starts. Because when the universe came into being, it should have destroyed itself immediately. In the earliest moments, matter and antimatter were created in almost perfect symmetry. For every particle of matter, a matching particle of antimatter appeared. Equal, opposite, destined to annihilate. And when matter meets antimatter, they erase each other completely. No debris, no leftovers, just pure energy. So the universe should have vanished in a flash. Yet somehow, it didn't. For reasons we still don't fully understand, matter gained a tiny advantage. A difference so small it feels almost meaningless. One extra particle for every billion. But that microscopic imbalance changed everything. After the annihilation ended, that faint residue of matter remained. Enough to form stars. Enough to form galaxies. Enough to form us. This is not a satisfying explanation. It is a confession of ignorance. We don't know why matter won. We only know that if it hadn't, nothing would exist to ask the question. And the mystery doesn't stop there. The universe runs on energy. But according to quantum physics, empty space should be overflowing with it. Vacuum energy, the energy of nothingness, should be so immense that space would tear itself apart faster than it could expand. Galaxies would never form. Atoms would never settle. Reality would dissolve before it could stabilize. Yet when we measure the universe, the energy of empty space is astonishingly small. Not zero, but so close to zero it feels deliberate, as if the universe were tuned, balanced on a knife's edge. A little more energy, and everything flies apart. A little less, and the universe collapses back into nothing. This balance has a name, the cosmological constant problem, and it may be the worst prediction failure in the history of physics. Our theories are off by a factor so large it defies intuition, a number with more than 100 zeros. Something is missing, something fundamental. And then there is gravity. Compared to the other forces of nature, gravity is absurdly weak. So weak that a small magnet can overcome the gravitational pull of the entire Earth. Yet if gravity were even slightly stronger, stars would burn out too fast. Slightly weaker, and they would never ignite at all. No stars, no chemistry, no life. Everywhere we look, we find parameters that appear delicately set, not optimized for life, but permissive of complexity. This does not mean the universe was designed, but it does mean that existence is fragile, precarious, unlikely. So here we are, standing inside a universe that by all expectations should not exist, governed by laws that barely allow it to survive. And the deeper we look into those laws, the more unsettling the question becomes. Was this outcome inevitable? Or are we living inside a rare exception, a cosmic accident that almost never happens? To answer that, we must look beyond our universe itself and confront the possibility that this reality is not the only one. Imagine a universe that never forms. No stars, no galaxies, no light, just expansion so violent that matter is torn apart before it can exist. This is not science fiction. It is the most common outcome predicted by our theories. Because the universe we inhabit sits on a razor's edge, and most possible universes fall off. Change the laws of physics just slightly, increase the strength of gravity by a fraction, and the universe collapses back into itself almost instantly. Reduce it, and matter drifts apart, forever isolated, never forming structure. Alter the charge of the electron, and chemistry fails. Atoms become unstable. Molecules never form. Adjust the nuclear forces inside the atom, and stars either never ignite or burn out in moments. The universe we see is not robust. It is precise, uncomfortably precise. This strange sensitivity has led physicists to an unsettling realization. The universe doesn't merely allow complexity, it barely tolerates it, which raises a dangerous question. Why this universe? One possible answer is chance, that we are living inside a rare cosmic lottery winner, a universe that happened by accident to land on the right combination of values. But chance requires repetition. You cannot win a lottery that is only played once. And this is where reality begins to widen. According to modern cosmology, the Big Bang may not have been a singular event. It may have been one bubble in a vast, ongoing process, a process called cosmic inflation. In this picture, space itself is constantly expanding, spawning countless regions that cool slow and become universes of their own, each with different physical laws, different constants, different outcomes. Most are sterile, chaotic, uninhabitable, but a few, vanishingly few, are stable enough to last. We call this idea the multiverse, not a collection of parallel worlds you can travel between, but an endless landscape of cosmic possibilities. If this is true, then our universe doesn't need to be special. We are simply inside one of the rare places where structure survives, where stars endure long enough for planets to form, where chemistry becomes complex, where observers can emerge. This idea is known as the anthropic principle. We observe the universe to be life-permitting because only such a universe can produce observers. It is a logical explanation, and yet it feels incomplete because it replaces one mystery with another. If countless universes exist, why does the multiverse itself have rules at all? Why does it produce regions with physics so delicately balanced? Why does anything exist anywhere? And there is a deeper discomfort. The multiverse may be fundamentally untestable. If other universes can never be observed, never measured, never interacted with, are they science or philosophy wearing mathematical clothing? Some physicists accept this uncertainty. Others resist it fiercely, because if the multiverse is real, it may mark the end of a certain kind of explanation, the hope that the universe had to be this way. And if the multiverse is not real, then the fine-tuning of this universe becomes even more disturbing, because then there is no cosmic lottery, no vast ensemble of failed universes, just this one, balanced, improbable, and unexplained. To move forward, we must look deeper still, not outward, but inward, to the nature of nothingness itself, because the next clue to why the universe exists may be hidden inside the vacuum. There is a place in the universe that should contain absolutely nothing. No particles, no radiation, no energy, a perfect vacuum. And yet it never is. According to quantum physics, emptiness is restless. Even in total darkness, even at absolute zero, space is alive with activity. Particles appearing and disappearing too quickly to be seen. They are called quantum fluctuations. Brief, violent, unavoidable. In this strange realm, pairs of particles and antiparticles constantly erupt into existence, borrowing energy from the vacuum itself. They annihilate almost instantly, returning what they took. But for a fleeting moment, nothing becomes something. This is not metaphor. It is measurable. These fluctuations leave fingerprints. Tiny shifts in energy levels, subtle forces between metal plates, small but real effects that can be detected in laboratories. The vacuum is not empty. It is the lowest energy state of a system that refuses to be still. And this creates a troubling possibility. If nothing is unstable, then perhaps the universe didn't need a cause. Perhaps existence is the default. According to some theories, the universe could have emerged from a quantum vacuum, not from absolute nothingness, but from a state with no space, no time, and no classical reality. A fluctuation, a spontaneous transition. In this view, the Big Bang was not the beginning of everything, but the beginning of structure. Time itself may have crystallized out of a timeless quantum state. Before the universe, there was no before, only possibility. But this explanation carries its own unease. Quantum laws describe probabilities. They describe what can happen. They do not explain why these laws exist in the first place. Why should there be a quantum vacuum at all? Why should obey equations instead of chaos? Even more unsettling, The energy of the vacuum may be responsible for the expansion of the universe today. Dark energy, a quiet pressure pushing space apart, accelerating the growth of cosmic distances. It is weak, relentless, and completely unexplained. The same vacuum that may have birthed the universe is now tearing it slowly apart. Galaxies drifting beyond reach, stars fading into isolation, a future of increasing darkness. And yet, the value of this vacuum energy is inexplicably small. If it were slightly larger, structure would never have formed. Slightly smaller, and the universe might have collapsed long ago. Once again, we find ourselves staring at precision, balance, unlikelihood. The vacuum does not answer the question of existence. It deepens it, because even the emptiest state imaginable is governed by laws that allow creation, laws that seem to favor something over nothing. And that brings us to the most disturbing realization of all. Maybe the universe exists because it cannot not exist. Maybe nothing is unstable by nature, and if that is true, then reality may be inevitable. But inevitability raises a final question. If existence is unavoidable, why does it look like this? To answer that, we must confront the limits of explanation itself, and the possibility that the universe is stranger than any cause we can imagine. At some point, every explanation runs out. Physics can tell us how the universe behaves. It can describe patterns with astonishing precision. But when we ask why those patterns exist, the equations fall silent. We search for deeper laws, a final theory, a single framework from which all forces emerge. Something inevitable, something that could not have been otherwise. String theory once promised such an answer, a universe where reality is woven from vibrating threads, each pattern determining the particles and forces we observe. But instead of uniqueness, it revealed abundance, not one solution, but a vast landscape, countless possible universes, each mathematically consistent, each physically different. Once again, we are faced with choice instead of necessity. Other approaches go even deeper. Some suggest that mathematics itself is fundamental, that the universe exists because it is one of structures that can exist. In this view, reality does not follow mathematics. It is mathematics, a self-consistent pattern that simply happens to be. But this raises a troubling thought. If all mathematically possible worlds exist in some form, what makes this one real? Why do we find ourselves inside this particular structure, governed by these constants, these symmetries, these fragile balances? There may be no answer. Or worse, the answer may be that the question is wrong. That why is a human instinct, not a cosmic requirement. The universe does not owe us meaning. It does not owe us inevitability. It simply is. And yet, it is hard to accept that existence itself is a brute fact, unexplained and unexplaining. Still, something remarkable remains. The universe is not only stable, it is knowable, its laws are discoverable, its patterns intelligible. From a tiny planet orbiting an ordinary star, minds made of atoms can uncover the structure of reality itself. This may be the most improbable fact of all, that a universe so finely balanced, so precariously assembled, also allows awareness, that it gives rise to beings capable of wondering why it exists. Perhaps that is the final clue. Not an answer, but a reflection. The universe should not exist, and yet it does, not just as a collection of particles and forces, but as a place where questions can be asked, where mysteries can be named, where silence can be noticed. Whether existence is a result of chance, necessity, or something we have yet to imagine, the mystery remains open. And maybe it must, because the moment we fully explain why the universe exists, we may discover that the explanation itself becomes part of the universe. Another structure, another pattern, another thing that exists without permission. The question is still there. Why is there something rather than nothing? And perhaps the most unsettling answer is this. There may be no final reason, only the fact that the universe continues. And so does the question,